Okay guys, welcome back. So today I'm going to talk about the topic of gravitation. So in the last series of videos I have been talking about the concept of mechanics. So I'll be continuing that for a while. And in the meantime I'll be also making some lessons on gravitation. So why is gravity important? Now you know that if you're standing on some plane, right? Some whether it's the earth or whether if you are going outer space or something like that, the weight is very important, right? So when you are in free space, it has a concept called weightlessness, right? Weightlessness. So that's also a concept of gravity that I'll be talking in the middle of the one of the videos in the series of videos I'll be preparing on gravitation about weightlessness. So gravity is important in order to hold objects in place, right? If gravity is not there, the objects will uh, not be in place. Means that say that if you have some car or something on some ground, right? Car is on ground or some car is on some elevated platform, its weight will be acting downwards. So weight actually depends upon the gravitational acceleration. So the gravitational acceleration of different planets are different. That you will understand when you will verse with the concepts of gravity. So the weight experienced by different objects at different instances or at different planets, or where the g the value of gravitational acceleration changes is different. So that will also I'll be talking in this series of videos on gravity. So that is the importance of gravity. Gravity is important to hold objects in place. Otherwise, now weightless is the process in which the gravity is absent, right? So weightless is also important in some cases, but for most objects, if you are working somewhere, if you are weightless, you can actually work somewhere because the objects are not in place. If you are working, if you are doing some math problem or something, or physics problem or something, if you are studying, sitting on a chair and working your sums on a table, if there's no gravity, the object will float in the air and you will also float in the air. So it is unable to do work because the objects are not placed according to the manner you wish. So gravity is important that way. So to understand gravity, you need to understand a special concept. So that concept, now you know that gravity of an object is due to actually not only one object, it's due to two objects. So one object has to be there, so that's the gravitational acceleration receiver, and the other one is the gravitational acceleration donor, right? So the gravitational, for example, if you are taking the system composing of a table and the earth, the gravitational acceleration donor, who is making the gravitational acceleration, who is providing the gravitational acceleration, is the earth. But the table is a gravitational acceleration receiver, because table is receiving the gravitational acceleration as provided by the earth. So there should be two objects so as to achieve a concept of gravity. So the gravitational acceleration receiver and the gravitational acceleration donor. All right. So as I mentioned, there should be two objects to receive gravity. All right. Now what it actually happens is that there's an attraction between these two objects. And that attraction is what we call the weight of that object, or that attraction is what we call the normal force of an object. So that depends upon the object, the position of the object, whether it's horizontal, whether it's vertical, or whether it's on an inclined plane, whether it's rotating, whether it's translating. That depends upon the position and how the object behaves according to time. So although for all those instances, the gravity plays a key role in keeping the objects at the place we want, right? So that's the importance of gravity. And to understand gravity, we have to understand a special concept that includes the a relationship as to how this force is dependent on various resources. So to understand that, we have to understand a special concept called the Newton's law of universal gravitation. So welcome to the topic of gravity and to the subtopic of Newton's law of universal gravitation. So Newton's law of universal gravitation. Right? Newton's law of universal gravitation. So that's the topic I'm going to talk about in this video. So what Newton was explaining was that if we have two objects like this, an object like this, right, and another object like this, so they should, according to this law, the masses should be different, but in some cases the masses are the same. So, if we have two objects like the force of attraction between two persons of similar mass, also we can put this, but I'm going to derive the relationship for two objects whose masses are different to each other. Alright, so I'll take another mass here like this, and I'll take the mass of the smaller object as a simple M and the capital object as capital M, right? And the force of attraction, now if you keep this object, now say this object is the earth, if this object is the earth, now the force of attraction is from this object towards the earth, so that will be like this, keeping this object at place. And if this object is the earth, the force of attraction is from this object towards the earth. So actually the force of attraction between two objects is a force that is building up in the same direction and equal in magnitude. Now it's actually regardless of the mass. Now you can say that the force is different because the mass is different. This should be something like F1 and this should be something here. I'll take the force here. This should be something like F2, F1 and F2 because the masses are different, but actually what happens is that the force of attraction is independent of the mass, right? The force of attraction is actually dependent on the mass. Now I'll derive the relationship. Now what I'm going to explain is that the force of attraction is the same for two objects whose masses and the densities are different. So the force of attraction is the same, but the force of attraction depends on the mass. The final solution for the force of attraction depends on the mass, but the force of attraction is the same regardless of the mass, the attraction between the two objects. Now I'm not talking about the final attraction, I'm talking about the force of attraction. Now these two forces are equal to each other, that's what I'm talking about. Alright, so Newton's law of universal gravitation. So what Newton said here was that if you have two objects like this, whose masses are different, say the first mass is simple m and the second mass is capital M, and the force of attraction between these two objects are F each other, right? The force of attraction between these two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between these two objects. So I'll take the center of mass of this object to be here. Okay. Right? And I'll extend that, and center of mass of this object to be here. And the distance between these center of masses is d. The distance between these two center of masses is d. So what Newton actually said was the force of attraction between these objects is directly proportional to the product of their masses. So the product of their masses will be the multiplication of these two masses, that will be m times n, and take as capital M times simple m, and inversely proportional to the square of the distance between these two masses. So F is inversely proportional, means F is directly proportional to 1 upon the square of the distance between these two objects. Is now the distance between these two objects is d, so the square of this distance is d squared. So as I derived in Newton's law about Newton's second law and the other concepts, and as well as you know that if you have two equations, two proportionalities like this, you can take it to a single proportion. So I can reduce it into a single proportionality, right? Single proportionality. So if F is directly proportional to m times n, and if is directly proportional to 1 upon d square, I can say F is directly proportional to m times m multiplied by 1 upon d square. So F is directly proportional to m times 1 upon d square. So 1 upon d square is actually dividing by d square. So this is actually equal to, F is equal to proportional to m by d square, right? M by d square. So in the laws of in the Newton's second law and the other concepts also, I told you that if you were to remove this proportionality, you have to equalize it with a constant. So what we can actually do here is we are not equalizing it to a constant. It is actually a constant, right? It's a constant that is measured according to certain experiments, right? Very finite experiments, right? So this proportionality has been understood that this proportionality is the same for any masses, and if the masses are at any distance between each other, say this mass is 20 kilograms, this mass is 100 kilograms, and this distance is 5. And another for another distance, if this mass is 8 kilograms, this mass is 60 kilograms, and the distance between these two are 75 centimeters, the value of the constant is the same for any both of these occasions, not for only 2 occasions, 3 or 4 or even million occasions. The value of the same, right? So F is what we call here is that F is directly proportional to m times m divided by d squared. What we are equating the constant we call the gravitational constant, right? The universal gravitational constant, and we denote it with a symbol called G. So what we can actually do here is that we can equalize this proportionality with the constant G. So F is equal to G times capital M times simple M divided by d square. So this is the equation that we are deriving for the Newton's law of universal gravitation, right? This is the equation. F is equal to G times M divided by d squared. So G is a constant for any two masses and for any distance between these two masses. So what is actually happening is that if the masses of these individual masses increases, the force of the force of attraction increases, and if the distance decreases, again the force increases. So to have a maximum force, you need to have the maximum mass of these two objects and the minimum distance between these two objects. Now if these two objects are on each other, right, on each other, so what it actually happens is d is actually very close to 0. Now d is actually not 0 because d is the distance between these two masses. What I am taking now, distance is the distance of the center of mass, right? Distance of the center of mass cannot be 0. So the distance to be 0, you have to make this value, right? This value, this center overlap this center. That you can possibly do in a practical situation. Now it may be theoretical, but in a practical situation it's completely impossible. So what you can actually do is you can overlap this surface with this surface, right? This surface with this surface. So d will be at its minimum. So when d is minimum, the force will be at its maximum, even if the masses keeping the masses, either masses constant or masses increasing. So therefore, to have the maximum force between these two objects, we have to make the masses, either both of these masses or an individual mass, as great as possible, and the distance between these two masses as closer as possible, right? Distance is very close and the mass is very high. So this is the Newton's law of universal gravitation. So Newton's law of universal gravitation is the basis of gravity. So you will understand that in the next video I am talking about the basic concepts of gravity. So in the next video and the series of videos thereafter, I will be talking about some complex theories. Actually they are not complex, although they are new to you, and it will be complex when I am explaining. Then I will simplify those and I will explain it to you with some examples. So hope to see you back, and thanks for watching this video, and see you again with another video on gravity.